All right, let's dive into something that sounds completely impossible, a real head-scratcher from the world of physics. We're going to talk about how something can be moving at an absolutely blistering speed, and yet, at the same time, technically be going nowhere at all. To do that, we need to learn the language of motion itself, kinematics. So let's start with the big puzzle right up front. Picture a Formula One car just screaming around a track. Its speedometer is maxed out, hitting an insane 360 kilometers per hour. And yet, I'm telling you that after one full lap, its average velocity is pretty much zero. How on earth is that possible? Well, stick with me because by the end of this, you're not only going to know the answer, you're going to start seeing the physics of motion absolutely everywhere. To crack this paradox, we need to play detective. We have to gather a few clues. And our very first clue is getting to the bottom of a fundamental concept in physics, the difference between distance and displacement. Now, they sound like they could be twins, but trust me, they describe a journey in two totally different ways. First up, we have distance. This is the easy one, the one we all get intuitively. It's the total ground you cover, simple as that. Think of it like your car's odometer. It just keeps clicking up, adding every single meter, every single kilometer, no matter how many twists and turns you make. In physics speak, we call this a scalar quantity, which is just a fancy way of saying it's a plain old number. That's it. Displacement, on the other hand, is a whole different beast. It's way more specific. You see, displacement doesn't care about the scenic route you took. It only cares about two things. Where did you start and where did you end? It is the shortest, straightest line between those 2 points. And because it's a line pointing from A to B, it has to have not just a length, but also a direction. We call this a vector. Okay, so let's put these two side by side so it really sinks in. Distance is the total journey you took, and it's always going to be a positive number, right? You can't untravel somewhere. But displacement, that's that direct line from your start to your finish. It's a vector, and it can be positive, negative, or, and this is a big hint, it can even be zero. Getting this difference is absolutely the first key to solving our big paradox. Let's make this super real. Picture this. You're walking to the market. First, you walk 30 meters to the east. You get to the corner. Then you hang a sharp left and walk another 40 meters to the north. Pretty simple trip, right? So what's your total distance? Well, this is a piece of cake. You just add the two legs of your journey together. 30 meters plus 40 meters. That gives you a total distance of 70 meters. Your legs did 70 meters of work. But now for the interesting part. What about your displacement? Remember, that's the straight line, as the crow flies, from your front door to the market. Well, if you remember a little high school math, it's the hypotenuse of that triangle you just walked, and it comes out to only 50 meters. But here's the crucial part. It's not just 50 meters. That's only half the story. It's 50 meters northeast. It has a number and a direction. Okay, clue number one is in the bag. We've got the difference between the total road traveled and the straight line journey. Now it's time for our second clue, and this one builds directly on top of what we just learned. We're going to tackle the huge difference between speed and velocity. Speed is exactly what you think it is. It's how fast you're going. It's what the speedometer in your car is showing you. To figure it out, you take the total distance you traveled, all those twists and turns, and you just divide it by how long it took you. And just like distance, speed is a scalar. It's just a number, like 100 kilometers per hour. Velocity, however, is speed's smarter, more specific cousin. Velocity is speed in a specific direction. So to calculate velocity, you don't use distance. No, you use displacement and divide it by time. And since displacement is a vector that has a direction, well, velocity has to be a vector too. So 100 kilometers per hour east, now that's a velocity. So let's lock this in because it's so important. Speed comes from distance, making it a simple number. Velocity comes from displacement, which means it absolutely must have a direction. This relationship, this one-to-one connection, is the real secret to finally solving our F1 paradox. We've got our two main clues, but every good mystery has a plot twist. There's one more piece to this puzzle, and it's a concept we all think we know, but its real meaning in physics is so much bigger. I'm talking about acceleration. So in physics, acceleration isn't just about slamming on the gas pedal. It's defined as any change in velocity over time. And listen closely to that word, velocity, not speed. Since velocity is a vector with magnitude and direction, guess what? Acceleration has to be a vector too. This means there are actually 3 different ways you can accelerate. You can speed up, that's the one we all think of. You can slow down, which physicists just call negative acceleration. Or, and this is the big one that trips people up, you can simply change your direction. That's right. Even if your speed stays perfectly constant, if you turn a corner, you are accelerating because the direction part of your velocity changed. Let that sink in. Anytime you change your velocity, whether that's by speeding up, slowing down, or just turning, you are, by definition, accelerating. So think about that F1 car. Even when it's going through a long, sweeping turn at a constant speed, it is accelerating the entire time. All right, detectives, we've got all our clues. We've got distance versus displacement, we've got speed versus velocity, and we know the true nature of acceleration. It is time to head back to that racetrack and crack this case once and for all. So let's visualize that racetrack one more time. What is the one defining feature of a single, complete lap? Well, the car travels a massive distance, maybe 5 kilometers or more, but it ends up right back where it began. The start line is the finish line. So I'll ask you, based on everything we've learned, what is that car's total displacement after it completes one perfect lap? Remember what displacement is, the straight line from the starting point to the ending point. You got it, it's 0, a big fat 0. Since the car started and ended in the exact same spot, its overall change in position, its displacement is nothing. It went nowhere, technically speaking. And here it is, the final reveal. The formula for average velocity is displacement divided by time. So, if the displacement for the entire lap is 0, and you divide 0 by any amount of time, you get 0. So while the car's average speed was incredibly high, its average velocity for the entire lap was 0. The paradox is solved. So, okay, we solved the brain teaser. That's cool. But this isn't just some fun party trick. This precise, careful distinction between speed and velocity, between distance and displacement, is the absolute bedrock for so much of the technology that runs our modern world. Just think about the GPS on your phone. It has to calculate your distance to estimate your arrival time, but it uses your displacement and velocity to know which direction to tell you to turn next. Or think about aerospace engineers trying to land a rover on Mars. They need to calculate the precise velocity, not just the speed of that spacecraft, to make sure it hits its target millions of miles away. Understanding motion with this level of detail is literally what makes modern life possible. And I'll leave you with one final thought to chew on. We now know for a fact that any change in direction is a form of acceleration. Right now, you're sitting on a planet that is spinning on its axis, while at the same time orbiting a star. Your direction in space is constantly, ceaselessly changing. So even though you might feel perfectly still, are you accelerating right now? Think about that. Thanks for tuning in.